All right, so the purpose of this lab, guys, is to investigate and prove, essentially, that the relationship in this formula is correct. Okay, that's what we want to find out. We want to find out the relationship or confirm the relationship between radius of a circle and the speed of the object going around in that circle. Okay, so we're trying to find out what's the relationship between radius and speed, okay, in this case. So that formula essentially. Now, are there lots of things that can affect the speed of an object as it goes around in a circle? Okay, obviously everything in this formula, radius, which is what we're trying to find, period, okay, anything else that can affect? Sorry, I still can't hear you. Okay, right, but that's the radius. Yeah, but you're right, it will. Okay, what else? What keeps it in the circle? Centripetal force. Centripetal force can also affect it. Okay, so what you need to be thinking about when you're kind of coming up with your variables here are what are the other things that could affect the speed of the rubber stopper in this case, and how do I keep them the same throughout the lab? Okay, and so obviously one of the things we want to keep the same throughout the lab is the centripetal force, because if we change that, then it's going to alter the speed, and we don't want to do that. All right, so the variables in this lab are the radius of the circular path. Okay, we're trying to find out its effect on the speed of the rubber stopper. Okay, so those are kind of the two most important ones. Okay, the mass of the rubber stopper is also important. Okay, because, well, we know this formula here, mv squared over r, okay, equals fc. V is in there, so mass could affect v. Okay. R, we already know R could, FC could, so all of these are things that need to stay the same. So in this lab also, okay, the rubber stopper will remain the same throughout the lab. Okay. All right, so mass of the rubber stopper, mass of the hanging weight. Okay, now that's not the greatest way to say that. I would say the mass of the hanging weight in this situation here. Okay, so if I didn't have this weight on here and I start whirling this thing around and around in a circle, am I even going to be able to whirl it around and around in a circle? No, because what's going to happen to it once I get it moving? Yeah, it'll just fly off, right? There's nothing holding it there unless I actually hold the string, in which I'm not going to be doing. Okay, in this lab, what we're going to be doing is allowing the radius to stay the same, only holding on to the meticulously engineered and crafted piece of PVC pipe. Okay, and then we want to keep the radius pretty much the same throughout. Everybody kind of follow me on that one? All right, so that'll be the trick to it. I make this look really easy because it's not my first time, okay? But getting it to stay the same radius is a bit of a trick, okay? Because you'll notice if I go faster, what happens to the radius, right? It gets bigger, right? Well, we're testing the opposite of that, right? So little things like that are things we're going to watch for. Now you'll notice, I don't know if you can see them or not, but you'll be able to see them up close. There are markings on the string, right? Those are going to be marking the radius of the circle, okay? And you want them to be where you can see them. Unfortunately, the person who did this one didn't do a very good job, because when you're whirling this around and around in a circle, it's really hard to see the top of the pipe. Not at this radius, but safely at this radius, it kind of is. Okay, so what I would say is when you're marking your radius, okay, so measure it there, that would be like about 20 centimeters or so. Mark it down here. That's the one you can see when you're whirling it around in a circle because it's at the bottom of the pipe. All right, so whoever did this one probably got smoked in the head a couple of times, okay, as a result of having measured it that way. Everybody with me there? All right, so that hanging weight is then putting the tension in the string, okay? And what about that hanging weight is putting, well, I actually kind of said it, the hanging mass is, right, force of gravity is pulling on it. That's what's putting tension in the string, all right? So without that, we'd have a lot harder time with this. Okay, so other ones here. So we have mass of the hanging weight, number of revolutions. We're always going to be doing timing the same number of revolutions because we don't want to just go once around and see if we can time that accurately. There's no way, right? So we're going to have it go around, I think it's 20 times, and we're going to time 20 revolutions, okay? And then just divide the time by 20, and we'll know how long one revolution is. Elapsed time, period, speed, okay, all of those are going to be in this as well. Now, some of these are going to change, right? And there's nothing we can do about that. We know that in this formula, okay, if I change this, these two numbers are probably going to change. I'm only really looking for the change in the speed, but obviously period is going to change as well. Okay, so there may be more than one responding variable. Everybody kind of follow me on that one? And it's okay to have more than one responding variable. We're just using one to get the other, right? We're going to use period to get speed in this lab. All right, so for our hypothesis then, okay, if and then statements, okay, the if part should talk about the relationship between radius and speed. Okay, the and part, as always, describes the experiment, okay, and the then part should tell me what will happen, okay, as radius increases, what will happen to speed. Okay. Okay, so the procedure is fairly straightforward. Okay, we're going to be looking at I've already kind of shown you how that's going to work, how the spinning part is going to work. So we're going to have 100 grams hanging off the bottom. Don't make it more than that. We need it to be 100 grams all the way through the experiment. So we're going to hold the string, okay, attached to the stopper at the 0 mark, okay, lay it on a table. Actually, that's not the way we're going to do it, okay? What we're going to do is we're going to lay it on the table, yes, okay, and we're going to measure the radius from the tube to the end of the stopper, but we're not going to mark it up here. We're going to mark it down below because that's where you'll be able to see it, okay? So just put your marks on there. If your thing already has marks on it, then just maybe mark one, do that one, then remeasure the next one and so on, just so you don't get confused with what's in here. Yes, the best, yeah. Rather than pull it to the right radius and start it, like you're going to hit yourself in the head, okay? You're probably going to hit yourself in the head anyway, but it doesn't hurt too badly. Now, the key to this, of course, even if you do get hit in the head to not getting injured, is to make sure you spin this the right direction. It is the rubber stopper that spins around and around the circle, not the 100-gram mass. Okay, that will end badly. I guarantee it. Okay, so yeah, start it out with the stopper just on the end of the pipe and then just start it. Okay, and then once you get to the right radius, then you just kind of keep it there. All right, it takes a little practice, okay, to kind of keep it at that radius. I'd be watching my mark, so I'm going to use this mark right here, okay, at the bottom. All right, so I'm going to keep it right there, do my best to keep it there. What you do not want to do at any point is go, oh crap, and pull this down, because then you're adding more centripetal force. Okay, we don't want to do that. If it's going to, if it's going out, then you're spinning too fast. Let it come back in a little bit and watch it. Okay, the key to stopping this without getting hit, there's a couple of techniques for that. Okay, so I've got it spinning right now. Okay, I would say probably the safest technique is after your 20 revolutions, reach up and grab it. Okay, or sometimes if you just go slower and slower and slower, it'll go right back into the tube. Okay, either one. I find that reaching up and grabbing it is probably the best way to not get hit in the head. Okay, if you would like eye protection while doing this, I can go get the goggles, but I've only ever had one person get a shiner doing this lab. I mean, and like that person could have got a shiner walking around in the hallway. Some people are just more accident prone than others. Okay. All right. So the radii that we're going to use are going to be 20 centimeters, 30 centimeters, 40, 50, and 60. Now, obviously, when we're putting those into calculations and stuff, they need to be in meters. So I would say just put them right in meters right off the bat. Put them in your chart in meters, okay, just so they're always in meters for you. And then, yeah, we're going to do 20 revolutions. Okay. Yeah, so it says here, put on your safety goggles. Okay. We don't have all of the instructions on there. Oh, there they are. Okay. Yeah, they're not all in there, but that's okay. So here's our chart. Okay, the time for 20 revolutions. Okay, so you're going to do it twice, just for consistency's sake, okay, eliminating sources of error by having 2 separate trials. So you'll have like 0.2 meters here, okay, in your chart you'll go like 0.20 meters, and then you'll have your time for 20 revolutions for trial 1, your time for 20 revolutions for trial 2. Add them together and divide by 2 to get your average time. Okay, then to get period, you're going to take this time and divide by 20. Okay, because it was 20 revolutions. That'll give you the period, and then you can calculate the speed using v equals 2 pi r over t. Okay, so that's how you'll fill in that chart. Pretty straightforward stuff. All right, and that's what parts 1, 2, and 3 are talking about there. Okay, so it's basically just telling you how to fill in the chart, which is what I just did. For number 4, identify the force that acted as the centripetal force and determine its value. So a little explanation and an actual number there for the value of the centripetal force. Okay, plot a graph of velocity versus radius. Okay, remember to plot the manipulated variable on the horizontal axis. Okay, and then a little bit of an explanation here, a couple sentences about what's the relationship between radius and speed based on your graph. All right, really, guys, like if you stay focused, you should be able to get this pretty much done today in class. All right, it's not due till Monday. I think I made it Monday. Okay, but it's not something that should be a ton of time for you. All right, as always, conclusion, restate your hypothesis, and then some explanation as to why it's acceptable or rejected. Okay, and then sources of error. There's a few in this one, right? And they're fairly easy to identify. Ways to fix them, less so, but you'll figure something out. Any questions? Okay, so everything you need is up here on the table. Just take a mass set. Don't just take the 100-gram mass out, take the mass set with you, okay, to your desk. And make sure you have clearance from other groups, okay? There's plenty of room for all of us to be able to do this in here. Just make sure you have clearance from walls and other groups when you're doing this, okay, just so that nobody's rubber stoppers meet in midair. Seen that happen. Makes a horrible tangle. You just end up cutting the string and starting over, okay? So we don't want to do that. Okay. Have at her. If there's questions, let me know.